Hello, everyone. A pleasure to see all of you. Okay, people are coming in. Excellent. Excellent. Can you can you hear me well? Type something in the chat if you can. Perfect. Great. Great, great, great. We are about to start. So yes, welcome to Compos. Welcome to Compos Year 10. We're pleased to greet you all. Just maybe a few words what we are and what we're trying to achieve. Okay. Maybe just people are pouring in. People are still joining. Okay, I'll wait for maybe 1 more minute. Okay. So, my name is Vlad. I have been running Compos for 3 years now. Our Compos director is a professor at Oxford University, Alexander Lvovsky, and he has come up with the idea for Compos. It's not a new idea. Similar schools have existed in other parts of the world for decades. So there was a school in USSR, for example, which existed for probably 70 years. So students like you would receive assignments by post because there was no email. Of course, they would receive by post. They would complete the assignment, send it off to the university. Tutors would mark that work and send it back to the students. And that was existent when I was your age. So I didn't participate, but my friends did. Okay. So that's one of things. Now it's obviously webinars, and you have tutorials in small groups, which are starting in mid-October. And some of you have already joined support groups, so I hope you enjoyed those. Right, this is recorded, so if you drop out or if you have to miss a session, don't worry. You can always rewatch the webinars. So my webinars is a small part of Compos, but I'll get to that. So why we're here? What we're trying to achieve? So imagine you want to become good at, or if you want to become an athlete. Okay. You don't at the age of 18 decide, oh, I'm going to athletics university and I'm going to become an athlete. After 3 years, I'm an athlete. It doesn't happen. You have to start much earlier. You have to start in, I don't know, when you're 8, probably 7, 8, 9. If you want to be an artist, the same scenario. You don't become an artist at the age of 18. You become an artist much earlier. Or if you want to be an actor, you don't become an actor. But somehow, if you want to be a physicist, you need to decide that when you take A levels, oh, I'm going to take physics, and perhaps I'll become a physicist. Well, that's a bit too late. That's what we think. We think if you like physics, you have to start early, and that's why Compos exists. You can come here, and we will train you to become as good as you possibly can in physics and maths. Okay, it's a tough journey, but at the end of Compos, for example, we have our first cohort. We have 50% went to Oxbridge. But we don't prepare for Oxbridge, right? We don't say we are here to make students ready for that. We don't do that. We just train you to become good at maths and physics. And if you choose to go to Oxbridge, then wonderful. If you don't, that's fine. Okay, it's fine with us. We just hope you enjoy the journey and you enjoy these two subjects, physics and maths. Perhaps we will add more subjects. We are thinking of adding chemistry, but it's proving a bit a lot of work to do that. So yeah, that's the intro. What will happen in the course? In this course, you have. Let me share my screen so you understand what I'm talking about. And if somebody's having problems, just share your link with them. That's perfectly fine. It's the same link for everyone. Okay. Share screen. All right. Can you see my screen? Just type 1 in the chat if you can see my screen. Perfect. So Compos. You have Compos year 10. You have 10 assignments. So that's 10 physics plus 10 maths. 10 physics plus 10 maths. We run from September to July. Now you have the webinars. That's every Monday. Sorry, not every Monday, but I will let you know. I will send reminders. So we'll skip some Mondays. Every-ish Monday. Then you have the tutorials in small groups, and those start in October, mid-October. You need to complete assignment 1 in order to be accepted to Compos. You need to do well. Usually we say you need to do above 50%. It might be slightly different. The passing grade might be slightly different for this year. Here in small groups. Or if you don't want to do in small groups, you can just join the follow along. And here, this is a self-study. And if you successfully complete that, you will also receive a letter notifying a letter from Oxford saying that you have completed Compos. And for example, you can progress to the next year automatically. You can join year 11 if you don't want to join year 10, for example. If you think it's a lot to ask. It's a lot of work, and it is a lot of work. We expect you to work 3 to 5 hours a week per week just doing the assignments. Then this is on top of the webinars and tutorials. Webinars are not mandatory. You don't have to come here, but hopefully that helps you complete the assignments. Okay. I can take a few questions right now. If you have a burning question, right, I'm happy to answer in the chat. Otherwise, we'll get to some physics. Okay, lovely. How do you submit the assignments? You will receive the recorded. The recorded are on our YouTube. So this is, you have the playlists, we have the Compos Year 10 webinars. You can watch last year's webinars as well. So these are last year's webinars. I've covered all topics. So how do I copy? So here you go. This is the link to watch last year's webinars. And and they will be published here. Perhaps I'll make a new playlist, or maybe I'll just continue the old one. No, probably I'll create a new list, but it won't be here on our YouTube channel. So this is the YouTube channel. I won't message that. Now, the assignments are submitted. The first assignment is submitted via a Google quiz, and you should have received a link, or you will receive a link in the very near future on how to submit that. Once you're in Compos, you will receive a login for Canvas. It is our Canvas course, and you will you will submit the remaining assignments, assignment 2, assignment 3, etc. You will submit in Canvas, and it will always be marked by the same tutor, and you will receive feedback in the short sessions, in the small sessions. All right, so welcome to Compos webinar 1, hydrostatics. And the question of the day: what is heavier, a kilogram of lead or a kilogram of wood? Okay, have a think about it, and I'll give the answer at the end of the session. If you okay. Well, they might be the same, or might be not. Why would I be asking? Okay. And just a quick intro. This is a wonderful book by Yakov Perelman. It's called Physics for Entertainment, or sometimes called Physics is Fun. Physics is Fun. So it's almost 100 years old, but this is how I got into physics. When I was 13, I found this book. Believe it or not, it was stuck behind my toilet. I don't know how it got there, but I started reading and I read it and I thought, wow, it's amazing. I loved physics, and I started studying physics, and that's how I got into physics. And then hence, yeah. So if you find it, you can download it, because the author died many years ago, so it's not covered by copyright, and you can download it and yeah, read it. Right, so problem 1, working with algebra in physics. I'm going to show you a few tricks that you should be using in your assignments. So it's a simple question. It's unrelated to hydrostatics, but that doesn't matter. What is the speed of the ball when it rolls down a hill? And we know that gravitational potential energy can be calculated. Gravitational potential energy can be calculated using the formula m times g times h. And the kinetic energy can be found using 1/2 mv squared. Now, the problem here that if you know that it is a conversion, even if you don't know, that doesn't matter. You know that gravitational potential energy at the start and kinetic energy at the end are the same. But if you try to calculate GPE, you won't be able to because you don't know the mass of the ball. Also, you need the mass of the ball to calculate kinetic energy, which you don't know the mass of the ball. So what do? We need to find gravitational energy and then solve an equation that kinetic energy is equal to that value. That's what you normally do in school. You have a formula, you try to substitute it in. At Compass, we teach you not to substitute until the very, very end. Don't substitute any values until you get the answer. So how would you do it in the Compass style? It's not Compass style, it's just physics style. So you would say, well, all right, so these two are equal. So mgh has to, okay, like gravitational potential energy has to equal to kinetic energy. And then that means mgh is equal to 1/2 mv squared. And you see that m, you can divide both sides by m. And because mass is not 0, you're not dividing by 0, so you're allowed to do that. You divide by m. And now you have an equation that doesn't contain m. And you don't know m. How lovely. So here, then I can multiply by 2. I multiply both equations by 2 and I get 2gh equals v squared. And now v is equal to square root of 2gh. And now I have found the answer as an algebraic expression. So the answer as an algebraic expression. And then you can substitute. The velocity is equal to square root of 2 times g, which is 10 on Earth, is usually 10 times h, which is 3. So it's a square root of 60, which is slightly less than 8. So I'm going to go with 7.8. Let's see if my guess is correct. Square root 60. 7.75. Well, close. 7. It's 7.7 technically. Okay. Meters per second. Can you explain again, please? Right. So in school, when you're asked to calculate gravitational potential energy, you would go mgh. But you don't know m, and you're stuck immediately. Like, how can you calculate gravitational potential energy if you don't know m? And same thing with kinetic energy. You can't calculate the kinetic energy because you don't know m. But because we know that these two are equal, we can equate them. mgh is equal to 1/2 mv squared, and then m cancels. And now it is an equation that has a solution because you don't need m to solve it because you can divide by m and m disappears. Does that make sense? Sorry, Helen, does that make sense or? Yeah, okay. Right, so another example of this. A ball is rising with constant speed. Find that speed. So these are the forces. There are 3 forces acting on the ball. This force is upthrust. upthrust. So don't worry, don't worry. You don't need these formulas right now. Upthrust, this is weight, and this is water resistance. Water resistance. So a ball is moving through the water. So let's say you have a ping pong ball. You put it under water and you let go, and it goes towards the surface. Okay. So these are the forces acting. And because we know that it is constant speed, that means that the total force is 0. Okay. So, but that means that these three forces cancel each other out. So we can say that in this particular scenario, the upthrust has to be equal to water resistance plus the weight. Because the forces are balanced, therefore the up arrow has to equal to the sum of the two. Forces are balanced. Because it's a constant speed. Because if the forces are not balanced, it would be accelerating. This will be covered in one of the next assignments. Like if you have a ball and you're pushing it that way and pushing it that way, this is forces 3 newtons and 3 newtons, you would have constant speed. If you have a ball 5 newtons and 3 newtons, it is accelerating. Okay, so here they have to be equal. So now you can say, okay, upthrust, there's a formula, so that's rho density G V, that's a volume, capital V, equals water resistance, which is KV, plus mg. And you need to find the speed. All right, so the speed is this expression. This is the speed. So KV is equal to rho liquid GV minus mg. And now you divide both sides by K and you get velocity. Sorry, velocity is rho GV minus mg divided by K. And all you need now is to substitute the values, which you probably have. But what I'm trying to show you, that when you do physics, you do it as algebraically. If you want a numerical answer, you take the final answer that you get and substitute the numbers in there. So even if you knew what the volume of the ball is, and if you knew the density, and you knew gravitational constant, you do not substitute until the very end. So that is the moral of the story. So the moral. Do not substitute numerical values until the very end. Okay, hope that makes sense. So this is, again, nothing to do with hydrostatics, just the way to do physics properly. I don't know. Anyways, moving on. Problem 3. Problem 3 is the hydrostatic law. It's not Pascal's law. I don't remember if it has a name. Anyways, the pressure in a liquid is the density of the liquid multiplied by the gravitational field multiplied by the depth. So what are the consequences of that? Well, the consequence of this equation, consequences, with a given density and gravity, I mean, if you're on the same planet, you're not moving to a different planet, the only factor is the depth h. So if you look at these three cylinders, there's a pressure meter attached to every single container. And you can see that the pressure in each container is exactly the same. Why is it exactly the same? Well, because the depth is exactly the same in each container. Well, not exactly, it's close. Well, sorry, doesn't matter. It is the same. The depth is the same, that means the pressure is the same. Because pressure is density, which is the same for everyone. The gravity, same for everyone. And depth, which is the same. Okay. So imagine you have a very weirdly shaped container. The pressure is due to the liquid pushing down. Of course, there's liquid above you and it's pushing down on you. Imagine, so if you go into a swimming pool, right? You dive into a swimming pool, you feel the pressure because there's water above you. So where do you think you'll have the highest pressure? At point A, at point B, or at point C? Very good. Yes. Well done. You have, because the shape of the container does not matter. The only factor is depth. And you can see that the depth here is bigger than here. And it's bigger than here. So A has the highest depth, therefore the highest pressure. Highest pressure is at A. What about the lowest pressure? Lowest pressure. Interesting. Lowest pressure. Is it C or B? Okay. Okay, I have anticipated different opinions on that. So on one hand, so the question is, which depth do we take into account? Do we take this depth, or do we take this depth? So which one do we use when we calculate? Because clearly, if you think about it, if you're standing at C, there's a lot of liquid above you. And if you're standing at B, there's not a lot of liquid above you. So which one is true? Well, it's actually C. It does not matter where you are in a liquid. The only thing that matters is the difference between levels. And I will demonstrate this with a simulation. So this is the simulation. And I'm going to use a pressure meter. And I'm going to place it at point C. And I'm going to place it at point B. And I'm going to place it at point A. And as you can see, the pressure at A is higher than B, and B is higher than C. So that is the solution. Liquid in a liquid, the pressure is distributed equally in all directions. And it kind of makes sense. Imagine a situation where the pressure, well, let's say there's a point D. D and B are on the same level. Imagine if the pressure at D was higher, then water would flow from high pressure to low pressure. The water would flow from D to B. There's nowhere to go. It can't go from D to B because, well, there's water in the way. That's a sort of an explanation. We can say it's hydrostatics, means it's liquids that are stationary. Yeah, so that's that. Okay, so we need to derive this equation. So where does this equation come from? So let's have a look. Imagine you have a column, you have a cuboid filled with water. So imagine, so derivation of pressure equals density, gravity times height. Imagine you have a container full of water, full of liquid. Right, so something like that. It has width, it has length, it has height. So the volume is W, length, height. Now we know that the mass of liquid, because mass, we know that density is mass divided by volume, therefore mass is volume multiplied by density. Mass of liquid is density multiplied by volume. But volume is WLH, so it's rho times WLH. Now we need the weight of the liquid. Liquid is mg, of course, mass times gravity. But mass, we've already established that mass is rho WLH. So rho WLH G. So the weight of the liquid is the density times width times length times height times G. Right. Now we need pressure. Pressure on the bottom. Pressure on the bottom is force divided by the area. I hope you know that from case stage 3. Pressure is force divided by area, but force, that's the weight. That's the weight divided by the area. What's the area of the bottom? WL, of course. Well done. So the area is WL, and the weight is rho WL HG. I hope you see where I'm getting at. WL cancel. And you have the pressure is rho HG. I'm going to rearrange it GH. That's the formula. So the pressure on the bottom is density times gravity times H. So a few more words about pressure. Pressure increases with depth. So the deeper you go, the more the pressure increases. And as you go up, the pressure decreases. Oh, what is that? Does anyone know? What is that pressure? That's atmospheric pressure, of course. That is the average atmospheric pressure at sea level. And look, if we go up, it decreases ever so slightly. It does decrease as we go up. As we go down, the pressure increases. Well, once we hit the water, it increases much more rapidly. So this is a cool simulation to play around with. And the meeting. We can switch off the atmosphere, and then you have 0. So you're in vacuum. And then the only thing that matters is the water pressure. And you can see it's much smaller now. Atmospheric pressure just goes 100 kilopascals. 101 kilopascals, technically. That's the value you can use. And all right. And so if you place a pressure meter at the bottom and you let the water out, the pressure drops as the water decreases, as the level decreases. What else? Of course, if you change the fluid density, if you change the density to honey, for example, the pressure increases. If you reduce the density, like gasoline, which is petrol, it reduces. Okay, so that's a cool thing to play with. Right. Any questions? Any questions on the formula? Does everyone understand what rho GH means? No, no questions here. Okay. Like honestly, just use 10. It doesn't matter. It doesn't matter what you use. You can give your answer in terms of G, right? So if the question was, what is the weight of a 10 kilogram stone, and you could say it's 100 newtons, you could say it's 98 newtons, you could say it's 98.1 newtons, or you can say it's 10 G newtons. All 4 answers are acceptable, right? It's fine. It's not important. It's not important what you use for G. It might be important in GCSE or A levels. That's why you rho is density. Density of the liquid. Rho is density of liquid. And rho is measured in kilograms per cubic meter. Well, I started with remembering that density is mass divided by volume. And from here, I worked out that mass is volume times density. But volume is WLH. That's the volume of the liquid. So so the mass would be the volume times density, which is rho times W times L times H. Weight, we know that weight is mg, mass times gravitational field strength. Therefore, the weight of the liquid is going to be rho WLHG. And the pressure is force divided by area, so it's weight divided by area, and area is WL. So WL divided by W, the whole thing divided by WL, WL cancels, and we're left with rho GH. Hope that makes sense. No, you're not expected to learn these formulas. You're expected to know this one. But we might ask you, I don't think it's not in the assignment, but this is the kind of question that you would be asked, I don't know, on an interview at university. Like, can you derive this? And you say, oh yeah, of course. The point is, the point of this exercise, imagine that you forgot this formula, P equals rho GH. Imagine that you forgot this formula. But you can work it out from here. It's four reasonably simple steps. You're expected to know this formula for GCSE, but not how the derivation. You expected to know this formula for GCSE. Well, you're of course expected to know this formula. And you're expected to know this. So pressure is force divided by area. That's another GCSE formula. Okay. Right. Archimedes force. So we're getting to the fun stuff. So if you've been bored so far, hopefully this will be more interesting to you. Like that. At Compass, we would probably give 2 marks for that. But yeah. Okay, Archimedes force. This is the force responsible for things floating. If you look at a duck in the water, the duck floats because of Archimedes force, which is also known as upthrust. So this is the water, and this is a duck. Okay, it looked much better in my head. Okay, that's a duck. And there's a gravitational force on the duck, the weight, and there's the Archimedes force or upthrust or Archimedes force. It is buoyancy, yes, it's also known as buoyancy. But I don't know how to spell buoyancy, so you have to I don't think you spelled buoyancy correctly. But yeah. Anyways, oh. Okay, so okay. Anyways, and there's the upthrust force, which is known as the Archimedes force, and the weight. So what is upthrust? Well, simply speaking, if you look what happens when you put something into the water, when something floats in the water, you have the shape of the water changes. Imagine you place a piece of wood on the water. So water. The water changes shape. The water wants to come back to its original shape. So it pushes out. It pushes the wood out. So it's pushing water out. That's a very, very simplistic explanation. So there's an upthrust force. Upthrust. A better explanation goes the following way. What is upthrust? We've already established that the deeper you go, the more the pressure. So let's see here. The deeper you go, the more the pressure. So I'm going to use this. So imagine we place, what can we place? A fridge. Image. I never knew fridges could cost £1,300. Anyways, we place a fridge in the water. Would a fridge float? I don't know. Depends. Depends what's inside. Okay. Now, water will push on the fridge. The water won't push from all directions. The water won't push from the sides. The water would push from the bottom. Would water push harder on the bottom or on the top? What do you think? Top or bottom? Where is the pressure higher? Why? Why is there more pressure on the bottom? Well, it literally shows us here. The pressure on the bottom is bigger than the pressure on the top. But the bottom is deeper, is at a greater depth than the top. So the pressure, you have high pressure, and you have low pressure. Here. That's it. That's Archimedes' force. That's the upthrust. That's where it comes from. Because the pressure on the bottom is going to be bigger than the pressure on the top, simply for the fact that the bottom is deeper in the water. And as you go deeper, the pressure increases. So, and that's it. The same true for hot air balloons. Look, if you take a pressure meter here, and you take a pressure meter here, you can see that there's a difference in pressure. So here you have high pressure on the bottom, lower pressure on the top, therefore that is an upthrust. 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 If you take a hot air balloon, hot air balloon, because there's more pressure. You can see here there's a lower pressure and higher pressure, because you're deeper in the air. Yes, as you go down, the atmospheric pressure increases. 323 and 303. There's a difference, and that means that the pressure on the bottom of the balloon is larger than the pressure at the top, and therefore there's an upthrust force causing the balloon to float. All right, the water is trying to dislodge it, so does it float or sink the fridge? You tell me. You tell me if it floats or sinks. Depends on what's inside. Helen, well, I don't know. What about ships? Ships are like ships are made of metal, but they float. My fridge contains 70 kilograms of tungsten. I don't know. You might misspell the tungsten. Is that? Yeah. It would probably sink pressure. Does high pressure try to move to low pressure? Well, no, it tries, but I mean, if you go vertically, there's high pressure on the bottom, but then there's the water on top that sort of prevents the water from going. But okay, high pressure. Many ships are made of. Okay, well done. Think pressure down some more. Thank you. Yes. Okay. Exactly had the same thought. That's interesting. I don't know. Well, the question is, if you want to know whether the fridge would sink or float, you have to compare the upthrust to the weight of the fridge. So if upthrust is greater than the weight, then it will float. If upthrust is less than the weight, then it will sink. And if it's exactly the same, then it will become a submarine. That it doesn't sink or float. So we don't know. Okay. And of course, so we've explained why upthrust happens. And now we need to know now we want to derive the equation for upthrust. The upthrust force is equal to the density of the liquid multiplied by the gravitational field multiplied by the volume of the object that is submerged. So L is density of liquid, G is gravitational field strength, and V is the volume of water, of liquid displaced. Because it's not enough to say it's the volume of the object, because the object could only be half in water, like a ship can only be half in water. So you only take the underwater part of the ship. So when we say, if you, let's say a ball floats in the water, by V, we only take this part. So this is the V. We don't take the whole volume. Density is the density of the liquid, and gravity is the gravitational field. Okay. And we want to derive that. We want, it's newtons, of course, it's a force. We want to derive that. So let's say we have the same cube. We have a cuboid placed in water. So it's a cuboid underwater, and this is H. And let's say that this depth is A, H, W, L. So let's say, suppose we have an aluminium block underwater. Right. So we need to calculate the pressure. So pressure at the top, and pressure at the bottom. Okay. So pressure at the top is rho g times the depth. So it's A because the rho g A. That's the depth of the top part of the block. The pressure on the bottom is rho g A plus H. What is the volume of liquid displaced? Now liquid being moved when from something being in it. How much of the object is in the water? Yes, thank you. All right, now upthrust force. So the area of the top is WL, and area bottom is also WL because it's a cuboid, right? It's a 3D shape. Now force on top is pressure multiplied by area. Yes, because pressure is force divided by area, so the force is pressure times area. So it's rho GA multiplied by the area multiplied by WL. The force on bottom is pressure times area, so it's rho G A plus H times WL. Now, but you would ask me, but there's a force on the sides as well. Why do we not consider the force on the left side and the force on the right side? They cancel each other out, of course. Well done, thank you. The ones that don't cancel each other out is the force from the top and the force from the bottom, because they are different, because the pressure is different. But on the sides is exactly the same. So force on top and the force on bottom. So the total force is going to be force from the bottom minus force on the top. So if you're pushing on the bottom harder than you push on the top, there's a resultant upwards force, which is F bottom minus F top. And we substitute that in. It's going to be rho G A plus H WL minus rho G A WL. This is rho G A WL plus rho G H WL minus rho G A WL. You can see rho G A WL cancels, and we're left with rho G H WL. What is HWL? Somebody? Volume. Well done. It's rho G V, and we got the we've found the equation. So the Archimedes force, or the upthrust, or the buoyancy force, upthrust force, thrust, is the density of the liquid multiplied by the gravity multiplied by the volume of the object that is underwater. You're not the whole thing, it's just the underwater part. L. L is liquid, is the index, is the density of liquid. It's not the density of the block, it's the density of the liquid. You can say AQ. Force on top is rho G. The force on the top is the pressure times the area. The pressure is rho GA because A is the depth, is how deep the top is under the surface of the water. So it's an A meters, sorry, from the surface. All right. By the way, you have access to the whiteboard. Anyone with the link is a viewer. Yes, and you can browse this whiteboard on your own whenever you like. It will also be published somewhere. Sorry, we are working flat out at the moment, trying to sort people into groups because year 13 has started, and we're trying to sort them into groups. So yeah, sorry if some things come delayed. Anyways, problem 5. Calculate the upthrust force on a balloon. The upthrust force on a balloon of radius 15 centimeters. So you have a balloon. Radius is 15 centimeters. Now, you also need the density. In this case, the density of the liquid, there's no liquid, you need the density of the air. Density of the air is approximately 1.3 kilograms per cubic meter. Right. So we need to calculate the force, the upthrust force on a balloon. Upthrust is the density of the air multiplied by the gravity on Earth multiplied by the volume of the balloon. Okay. The volume of the balloon, if it's a sphere, it's 4/3 pi r cubed, which is, so we can substitute that, so density of the air multiplied by the gravity multiplied by 4/3 pi r cubed. You see, I have not substituted any values yet. I only do it at the very end. So that will be density of air, which is 1.3, multiplied by the gravity, which is 10, multiplied by 4/3, multiplied by pi, which is 3.14, multiplied by r cubed, which is 0.15, because it has to be in meters, 0.15 meters cubed. All right, now I put that in my calculator. 1.3 times 10 times 4/3 times 3.14 times 0.15 cubed, 0.18 newtons. Will it float? Will my balloon float? Cheyenne, brilliant. Thank you. Of course, it will float is the weight. If weight is less than 0.18 newtons, it will float. If weight is greater than 0.18 newtons, it will not float, it will sink. Imagine it was made of metal. I never told you it's an air balloon. Maybe full of water. And then the weight is I don't know, 10 newtons, 20 newtons. That's the thing. There are two forces, the upthrust and the weight. And if upthrust is bigger, it will float. If the weight is bigger, it will sink. You don't need the upthrust formula for GCSE, no. But you need it for compos. What about a hot air balloon of radius 4 meters? Well, let's calculate. So we have a hot air balloon with a basket, of course. So the radius is 4 meters. And we have upthrust because it's in a fluid. The balloon is in a fluid, in air. It's rho GV. So it's rho times G times 4/3 pi r cubed, which is 1.3 times 10 times 4/3 times pi 0.14 times 4 cubed. And I believe 4 cubed, which is 3,480 newtons. Okay, 10. G is approximately 10. G is 9.8 on Earth, newtons per kilogram. That's the gravity on Earth. Gravity on Earth. This value, the density of air, well, it's an empirical value. You can measure it. If you take a cubic meter of air, it will have a mass of about 1.3 kilograms. So 1 cubic meter of air is approximately 1.3 kilograms. You can also prove that mathematically, and this is something year 11s are doing at the moment. So if you can carry on with compos in year 11, the first assignment will be, one of the questions will be that, to calculate the density of air. And now you can see that the balloon has a much bigger upthrust. Therefore, it will float if its weight is less than 3,000 newtons, 3,480 newtons. So basically, if it can have a total mass of 348 kilos-ish. That's the maximum mass of a balloon in order for it to float. Okay. Does that make sense? By the way, you can watch my old webinars. I go into the same topic at a slightly different approach, angle, so feel free to watch the old webinars as well. All right. Problem 6. Two liquids with different densities. Oh, sorry. My name is Vlad. Yes, Vlad. You can see my name on the assignment. Okay. Now, problem problem 6. If you pour two liquids with different density into a glass and place an object with density rho, which is greater than the bottom liquid but less than the upper liquid, it will float in the middle, as you can see. So there's water, oil, and there's a cork, of course, cork. There's a stone, and there's a Lego brick, Lego. And you can see that Lego is in between the water and the oil. That means that the density of the Lego is less than the density of the water, but greater than the density of the oil. Quite cool, quite an experiment. And this is the same experiment taken to the limit, I guess. It has all sorts of liquids, honey, corn syrup, yeah, maple syrup, milk, etc. No, we're not having a break. We're just going until 7:30. Okay, now we are so the question is, so you have two different liquids. This is the boundary. So liquid 1, liquid 2, liquid 2, and there's an object floating here. The question is, well, this is V1 and this is V2. The different parts of the object are in the liquid, V2, and yeah. So what we need to find is V1 to V2. What is the ratio? Okay. So what we can do is we can treat the two parts differently. We can treat this part, V1, and we can treat this part separately, V2. And let's find the forces acting. So of course, there's the weight, and there's the upthrust. And same here, the weight and the upthrust. Ooh, no, sorry, you can't do that. I realized that this is no good. No. Okay, let's do it this way. Here. So there's the upthrust from the liquid one, pushing up. There's upthrust from the liquid 2, pushing up. There's the weight of the stone. Weight. That works. Okay. So the weight of the stone is equal to upthrust from liquid 1 plus upthrust from liquid 2. This will be uploaded to YouTube probably today, tomorrow the latest. We know that the weight is mass mg. Upthrust 1 is going to be the density of the liquid 1, rho 1, g v1 plus rho 2 g v2. And immediately we can see that we can divide by G, and G cancels. But on the other hand, what is M? M, mass of the stone, is the density of the stone multiplied by the volume of the stone. But the volume of the stone is V1 plus V2, equals density times V1 plus V2. You can substitute that in here. So density of the stone multiplied by V1 plus V2 equals rho 1 V1 plus rho 2 V2. Okay, and now rho V1 plus rho V2 equals rho 1 V1 plus rho 2 V2. And we need to find the ratio of V1 to V2. So we take V1 to one side, V2 to the other side. So V1 rho minus rho 1 equals V2 rho 2 minus rho. And now we divide both sides by V2. So V1 to V2 is equal to rho 2 minus rho, and we divide by rho minus rho 1. Rho minus rho 1. And this is the answer. So when you study physics at a high level, your typical answer looks like this. Answer V1 to V2. Rho. Look, it says rho oil, rho Lego, rho water, density of the liquid, density of the solid, density of the stone, etc. Yeah, so it's just an indicator of what are we referring to, because everything has density and you want to know which density you're talking about. So here you have three densities. You have the density of liquid 1, you have density of liquid 2, and you have the density of the rock, of the object. It's not an rock, it's just that. And this is the answer. Okay. Right. Now. Yeah, so don't worry if you don't fully understand this one. Sorry? Okay. Now, getting back to the question of the day. Has anyone figured it out? Has anyone figured it out? The question of the day was, what is heavier, a kilogram of lead or a kilogram of wood? Well, we need to figure out what we mean by heavier. Lead is denser, indeed, yes, but are they the same? They certainly have the same mass. If I said, which has the same bigger mass, a kilogram or a kilogram of wood, it certainly is the same. So mass, they have the same mass. Mass. Same weight. But when we say heavier, what do we actually mean by heavier? Is that in everyday life? This is heavier because it has more weight. I have just shown you that the hot air balloon hot air balloon can have a mass of 300 kilos, 300 kilograms. So a hot air balloon is 300 kilograms. And a piece of lead, let's say 1 kilogram. So which is heavier? Do we say that the hot air balloon is heavier? But it floats in the air. How can it be heavier? How much force is needed to lift it? Yes, that's what we mean. When we say what is heavier, which requires a bigger force to lift? Which requires a bigger force to lift? This is what we mean when we say heavier. Okay, I'm playing with words here. I'm playing with the word heavier. Of course, it could mean different things. But normally, in everyday language, when we say heavier, means which is easier to lift. Now, you would think that they're equally as hard to lift because a kilogram of lead and a kilogram of wood. But what if... Ooh, Sasha, very nice. You're onto something. So what? Can you carry on? Displaces more air. And the buoyancy force on wood is higher. Yes. Remember, I said, what is the upthrust force on a balloon? It is about 0.18 newtons. It's a small force, but it's there. Any object placed in air will experience an upthrust force. Any object placed in air placed in air experiences upthrust. Bigger objects displace more air. So if you take a piece of lead, it's going to be a very small piece of lead. And wood is going to be a large block of wood. So the upthrust force on lead is smaller than the upthrust force on the wood. It's not going to be a large force, but it's going to be a small force. So the upthrust and the upthrust here, upthrust on lead and upthrust on wood. Because they have the same weight, but larger upthrust on wood. So wood is easier to lift by a very small fraction, but ever so. No, upthrust is simply the force of the air pushing the wood out. Look, imagine imagine a 1 kilogram hot air balloon. So this is 1 kilogram, this is 1 kilogram, and this is 1 kilogram. And if it's filled with hot air, which one is easier to lift? The lead or the hot air balloon? Yeah, of course. Some hot air balloons, you don't even need a force to lift it. It just goes. You actually need a negative force to hold it back. So this is the extreme case. But wood is bigger than lead. It's about 10 times bigger. A piece of wood of 1 kilogram would be approximately 10 times bigger than lead. Therefore, it will have about 10 times more upthrust. So the upthrust will help you lift it. Upthrust is proportional to volume, yes. The bigger the volume for the same mass. So if you keep them, bottom line is, if you take an object you keep the mass the same, but you make it bigger and bigger and bigger. At some point, it won't float. What if the wood is carved so that the surface area of the water on top is the same as the lead? It doesn't matter. The surface area, it doesn't matter. There's the volume matters. Remember, the upthrust is equal to density of the liquid, density of the fluid, times the gravity times the volume, and that's it. Bigger volume means more upthrust. Okay, so technically lead is heavier. So it's 1 kilogram of lead is heavier than 1 kilogram of wood. I got this example from the book that I've showed you in the very beginning, but they had a different reasoning, and they concluded that wood is heavier. But I disagree. With that, but I agree with most parts of the book. Okay, I'll finish here. I hope this was informative, and I hope this was enjoyable. Now, as I said, to get onto the compost course, you normally need about 50% completion of the first assignment. It might feel like an arduous task, but yeah, I hope you I hope you I hope you enjoy doing it. And even if you don't get in, you can still attend the webinars. You can still come along. You can do the follow along program. So yeah. Okay. So right. Okay. Yes, you can switch off now. Thank you. Thank you for your attention, and see you next week for some maths. Ben, if you're still here, you've asked a question. You can ask questions, but nobody's supposed to solve it for you, if that makes sense. You can ask, you can get all sorts of help, but as long as nobody's helping you to do the assignment, the questions themselves. So with that, you can discuss amongst each other, but it has to be your own work. Okay. All right. See you. Where can I do the follow along? We will, because you're on this system already, we will invite you to the follow along at some point. Yeah, just we don't have a formal follow along. You can join it. Basically, everyone joins the follow along automatically, unless they want to opt. Okay. See you. With the math question, does it matter what method I use? Well, in questions where it says use this method, yes, it does matter. For questions that where it's not said which method you use then normally it doesn't. So that's the rule. Unless your method is using ChatGPT and we wouldn't like that. use ChatGPT by all means, but it can't be. Your solution can't be based on that. I didn't have some question about searching up the gravity of Venus. Cheyenne. Let me have a look. So, question 7. Question 7. When the mass of Venus is atmosphere of the Venus. Pressure. No, you don't need any other. You don't need any other information. You just need the surface area and the pressure. It's actually a very simple question, like two-step question. Question 4, without knowing the gravity of the Earth. Estimate. Yeah, you do need the radius of the Earth. You can look it up. For question 4, we expect you to look up the radius of the Earth, yes. You Blanca, well, yes, you're expected to look things up, but for example, you can't look up the mass of the atmosphere of Venus. That has to be your calculation, right? So you can look up gravity of Venus if you wish. You can look up the radius of Venus. You can search up yeah, the average density of the atmosphere. But you can't, in that particular question, you can't use the density of the atmosphere because you are expected to just using these two values to calculate. But look, give it your best go. We will give you as many marks as we think you deserve. Like even if you didn't know how to do it and you looked something up, just write, I've looked this up, and from here I can deduce that. We'll give you as many marks as we possibly can for that. Okay. All right. See you.